Very good evening to one and all. And on behalf of the National Academy of Sciences India Delhi chapter and the host institution, the Upadhyaya College, University of Delhi, I welcome Professor Vincent Poor, who is a fellow of the Royal Society, and Michael Henry Strater University professor at Princeton, as well as all the students, researchers, and faculty members who have joined for this special public webinar, which is jointly organized by NASI and the Upadhyaya College under the aegis of the DBT Star College program. And it's basically a joint science promotion initiative of the two organizations. And Professor Vincent will be talking to us today on the topic towards 6G wireless communication networks, vision, enabling technologies, and new paradigm shift. And I also would like to thank Professor Anurag Sharma, who's the chairperson of the NASI Delhi chapter, and the president of NASI, Professor Ajoy Kotak, who have been a source of inspiration and always have been there with us for organization of these kind of activities. So before inviting Professor Vincent to deliver his talk, let me briefly introduce him to all of you. He's a Michael Henry Strater University professor at Princeton University, where his interests include information theory, machine learning, and network science, and their application in wireless networks, energy systems, and related fields. During 2006 to 2016, he served as the dean of Princeton School of Engineering and Applied Science. Prior to joining Princeton in 1990, he was on the faculty of the University of Illinois and has also held visiting appointments at several other universities, including Berkeley, Cambridge, Harvard, and Stanford, among others. Among his publications is the forthcoming book, Machine Learning and Wireless Communication, to be published by Cambridge University Press. He's a member of the US National Academy of Engineering and the US National Academy of Sciences, and is a foreign member of the Royal Society and other national and international academies. Recognition of his work includes the 2017 IEEE Alexander Graham Medal and honorary doctorates from a number of universities in Asia, Europe, and North America. With these words, I now invite Professor Vincent to kindly share his screen to deliver his talk.
Thank you very, can you hear me okay?
Yes, perfect.
Let me go with full screen. How can you see that?
Yes.
Okay, fantastic. Okay, well, good evening, everyone. Thank you very much, Manoj, for that lovely introduction, and also for the invitation to speak this evening. I'm really honored to have this opportunity, and I look forward to hearing your questions and any dialogue after my talk. So today I'm going to talk about 6G wireless. And you might wonder why I'm talking about 6G wireless when we are just now rolling out 5G wireless. Just a bit of history. You know, the history of the modern era of wireless has been that about every 10 years, a new generation of wireless systems rolls out. So 1G, which I'll talk a little bit more about these later. 1G rolled out in the 80s, 2G in the 90s, 3G about 2000, 4G about 2010, and so forth. And 5G just rolling out now. So we can expect that in another decade, maybe a little less, 6G will be rolling out. And basically what happens is that even though each generation has the latest, greatest technology, what happens is applications come up that sort of use up all the capabilities of a given generation of wireless. And so we need to provide new technical capabilities so that we can accommodate new applications. And engineers aren't always able to anticipate what those applications are going to be. But basically that's why I'm talking about 6G, is because now that 5G is standardized and it's being deployed, although it's still being improved, researchers like myself are starting to think about, well, what kind of capabilities might we provide in 6G? So that's what I'm going to talk about today. Of course, nobody really knows what 6G is going to be. So this is really just a vision for what 6G might be, some of the technologies that we might need to enable that vision, and then what some of the big picture paradigm shifts may be that will be necessary in 6G. Now, what I'm going to talk about is based on a paper that appeared in Science China last year with updates. This is an evolving thinking. This is evolving thinking. But that paper is one that has many authors. So what I'm going to talk about today is really the distillation of many minds thinking about 6G. So this is not just my ideas, this is the ideas of many people. And I've discussed over the years since this paper was published, I've discussed the ideas with some of these colleagues, and our thinking is evolving. But I think some of that evolution is finding its way into my talk today. So let's get started. So just keep in mind, there are a lot of people thinking about something that we don't really know exactly what it's going to be, but we're thinking about, these are some of the people who are going to develop the ideas into technologies that could make it happen. So that's basically what the background, I would say, of what I'm going to talk about today. You can take it with that spirit. So here's the outline of an outline of my talk. First of all, a bit of motivation. Why are we talking about 6G? I've already talked a bit about it, but I'll be a little bit more technical about that. Then I'll talk about some of the performance metrics and application scenarios that we might see in 6G. Then I'll talk about some enabling technologies, some of the things we might be able to develop that will help us to perform, help 6G systems perform in the way we'd like them to. And then some of the big picture paradigm shifts that will likely will possibly go along with 6G evolution. Then I'll wrap up and be happy to take questions after. Just by way of motivation, first of all, what do we have in 5G? It's worth thinking about that first before we start thinking about what we might need in 6G. Well, of course, in 5G, we have all the things we had in 4G. Those are there. We didn't throw anything away, but we also have some new capabilities. One is enhanced mobile broadband, and this means basically gigabit per second mobile broadband. So very high rates for very high download speeds to your mobile phone. Massive machine type communications. That is, unlike in previous generations of mobile communication networks, where the end users are humans. In 5G, we also have the scenario where the end users are also machines. So that means that there can be many more users in a given geographical area. So we have so-called massive machine type communication. So this brings in all kinds of other requirements. Certainly the massivity of it brings in requirements for capacity, but also because we're communicating with machines, we need ultra reliable and low latency communications. And I'll just focus on the low latency part. Latencies from 4G back were based on human perception. So latencies of 100 milliseconds, for example, were considered adequate because humans can't perceive time frames less than that. But machines can. Machines can conceive very low latencies. And some of the applications of mobile communications, like autonomous driving, require latencies much shorter than 100 milliseconds. So that's the idea behind URLLC. And I'll talk more about that because I think this is still evolving in 6G. So there were also some key technologies that were developed for 5G. One is millimeter wave. So, 4G and back, are microwave systems. In the intervening time since 4G was rolled out, the devices at the millimeter wave have been improved so that they're commercially feasible and technically sound. And moving into the millimeter wave has allowed us to get a lot more capacity. The millimeter wave band, I should say, has given us a lot more capacity. Another technology is massive MIMO. So of course, MIMO, multiple input, multiple output, or multiple antenna systems, was an advance in 4G, giving us much greater capacity. And then massive MIMO, so this means MIMO, I'm sure most of you know, but it just means you have multiple antennas on both transmitter and receiver. This gives much greater capacity. Massive MIMO is an extreme of MIMO where this is usually on the transmitter or on the base station, if you will, the number of antennas is massive. So, on the order of 100, say. And this allows much greater performance. And this is an advance of 5G. And then finally, ultra-dense networks, which is to support the massive machine type communications. These are networks where there are many users in a small geographical space. So you might think about these users as being sensors, actuators, things of that sort on a factory floor. So an automated factory where there's a lot of machines, including the sensors and so forth that monitor them. Okay, so this is what we got in 5G. It's great. There's going to be a decade of finding the best ways to take advantage of these technologies and all this capability. And that's what's going to be happening over the next decade in the application side. But in the research side, we're already starting to think about what's next beyond these technologies, beyond these scenarios. So why do we even need that? This is already quite good. Well, first of all, 5G it's surely going to be the case, if history tells us anything, that 5G is not going to meet all the requirements in the decade ahead of us, 2030 plus. Okay, and this has just happened every 10 years. We're pretty sure it's going to happen again. So in addition to the guaranteed latency provided by 5G, 6G is also going to require much tighter time and phase synchronization accuracy. Okay, and that's going to be partly to support machine type communications where very short times, very tight phases can be very important to the operation of certain automation systems, control and feedback and so forth. 6G also needs to provide nearly 100% coverage. That's because of some of the applications like autonomous driving you can't just go into a dead zone if you're going to be using autonomous driving, for example. And sub-centimeter geolocation accuracy. This is to support, the latter is to support something like robotics on the factory floor, where you need to know very accurately where each asset is. Other applications, like, I mentioned this gigabit download speeds for 5G, but that's not enough for some applications like 3D video, for example, virtual reality, augmented reality. These really require terabit per second, that is trillions of bits per second transmission data rates, while 5G can really only provide gigabit per second. By the way, those of you who've been around a while will be amazed at the gigabit per second rates that we have today. Certainly, 30 years ago or even longer, when I first got involved in cellular network research, I would have never thought we could have gigabit per second systems. So I'm confident that we will get to terabit per second too, just because I think innovation continues to produce new ideas that allow us to pack more and more capacity into the ether. And then finally, one of the most important things is that faced with big data sets, so we're thinking about sensors. Of course, even smartphones now have many sensors on them, but sensors will be part of the network. A lot of data will be collected at the edge of the network. So big data sets will be collected. The scenarios will be more and more diverse, particularly because of machine type communications and new services. So artificial intelligence is going to play a much greater role in services and in managing the network and so forth. And I'm going to talk more about that going forward. So other things, well, as I mentioned before 5G, traffic on cellular networks was really dominated by video streaming, right? That's the big capacity hog on current networks, okay? But for 6G, we can expect new applications, okay? And I already alluded a bit to robotic mobile robots, and of course they have to be controlled over the network if they're going to be mobile. So that means we need to have distributed control systems, and they're because the scenarios are so varied and the environments are so varied, using models to design those systems is not necessarily going to be possible. So AI is going to become important. Okay, so this is just an example. So an example of of course a robotic object is an autonomous vehicle. Another example, of course, is a factory floor where you have robots taking materials, putting together things, doing welding, and so forth. So these kind of applications are going to require very, very high level of performance. So let me talk about some of those performance and some of the applications that can ensue. So some of the performance metrics that people have talked about are here. These are not necessarily compatible with one another, and they're not necessarily what is going to happen, but there are some things that people are talking about and may shoot for. So one, for example, is, I mentioned already, is peak data rate of about a terabit per second. So 1 trillion bits per second. And this is to support some of these very high end video and like 3D video and virtual reality and things like that. Very high connection densities, 10 million devices per square kilometer. This is massive connectivity, even more massive than conceived in 5G. Very, very tight latencies, less than a third of a millisecond, very difficult to obtain. And by the way, this requires, a new thinking about networking, because even network delay can be more than that. So there's a lot to do to get to this level. Very high energy efficiencies, and this is, and very high spectral efficiencies. And so energy efficiency and spectral efficiency are competing criteria. So, this is going to require some new thinking about how we design networks, and they may not be possible to increase energy efficiency 100 times and spectral efficiency 10 times as well. We may need other methods like going to even higher frequencies and so forth. But these are targets. And then very tight positioning accuracies, again, for things like indoors, for things like robots, outdoors, for things like automobiles. Okay. Some application scenarios we might think about for 6G, well, strengthen 5G scenarios. Everything we're doing now, or we're going to do, thinking we're going to do for 5G, do the same, but better in 6G. Also new scenarios, well, human-centric services. So what does this mean? Well, this has to do with thinking about networking, not from the point of view of criteria like data rate or latency, but to think about the criteria that maybe matter more to humans in certain situations, like privacy, security, and so forth, designing those into the network from the beginning. And you might think, for example, about a body area network where you have monitoring devices, to health monitoring devices on your body. Well, you certainly would like to keep that private. So privacy is an essential part that needs to be built into the network. Industry 4.0 in robotics, I've already talked about advanced automation, having mobile robots, having 6G networks in the factory, running the automation, and then convergence of communications, computing, control, localization, and sensing. So you've got all these different things today in systems, in cyber systems. And so you have a physical system, so you have a cyber physical system. And on top of this physical system, there's a communication network, there are computers, there's a control system, there may be localization if it's robotic circumstances, and you've got sensing, of course. And these are all different systems. So one of the things we're going to see is a convergence of some of these systems, maybe all of them, but certainly, for example, communications and sensing are starting to converge already. And then integration of different kinds of networks. And I'm going to talk more about this later. So today we have satellite networks, we have drone networks, we have terrestrial cellular networks, we have ocean going vessels with their own networks. So all these are different networks, but to get universal coverage, we might need to think about integrating all those into one big network. And then finally, as I mentioned earlier, distributed AI. So, AI throughout the network. So applications at the edge, monitoring the network, optimizing the network, and so forth. And I'm going to talk more about that as we go through. So what are couple of examples? Well, one is cloud virtual reality. So, I think everyone knows what virtual reality is, but it's basically a simulated experience that can be similar to or completely different from the real world. So you put on the virtual reality goggles and the computer creates a world for you to experience. And that, as you can imagine, takes a lot of computing power for that to happen, because it's 3D video, audio, and it's all happening in real time, right? So for immersive experiences, you need very, very high level of computing power, very high performance. And if that's in the cloud, then you've got an issue of latency, because if you need to upload data to the cloud and download the experience parameters to your virtual reality goggles, that's going to take a lot of time. So reducing latency is a very big challenge for cloud VR over wireless. Okay, so that's one of the big challenges here. Industry automation, I've already mentioned it a few times. The idea behind Industry 4.0 is to enable industrial production with greater flexibility, utility, and efficiency based on cyber physical systems, as I mentioned before. So here, the Internet of Things is the supporting technology, and basically the idea is things are the end users, as I mentioned before, rather than human beings. And we need ubiquitous connectivity in order for that to happen, because when you're running a factory, you can't have outages, you can't have dead zones. Everything has to work and everything has to be connected all the time. Now, a challenge in industry automation, unlike other aspects of wireless, is that, factories have long lives. You build a factory, it's there for 50 years, just to amortize the cost of building it. It's a very intensive, capital intensive investment. So it's not like we're going to be able to build new factories for 6G Rather, we're going to have to be able to take existing factories and integrate new technologies into them. So this is so-called brownfield installation as opposed to greenfield installation, which we normally would do for normal cellular networks, where we just replace base stations with new base stations, sell new mobile phones. That's greenfield upgrade. We can't do that with factories. Factories, we have to take the physical infrastructure that exists and overlay new cyber infrastructure. So some of the use cases, though, are very powerful. Mobile robots, okay, so helping make factories more efficient and safer. Remote maintenance, that is maintaining the factory equipment more effectively. And then just in general, managing plant assets like inventory and so forth. So all these things can be made much more efficient with the right cyber infrastructure. So what are some of the enabling technologies that might help with some of the requirements that we foresee for 6G? Well, I'll talk about two things. I'll talk about the air interface, and then I'll talk about networking. Okay, so at the air interface level, I'll just remind you, if you're familiar with the evolution of cellular networks, that it's largely been a story of evolving physical layer access techniques. So 1G, the first generation of cellular networks was basically an FM analog voice network. And then 2G was a digital voice network using time division multiple access, TDMA. And it also allowed texting. Okay, so that was 2G, it came out in the 90s. And then 3G, which was in the 2000s, had two air interfaces. One was another TDMA air interface, GSM, and the other one was CDMA. So there were two competing air interfaces. If you remember those days, you had to be careful you got the right kind of phone for your network. And that allowed email, okay, so wireless data services. And then 4G, we switched to orthogonal frequency division multiplexing, OFDM. And that's when we got web browsing on the internet. And that's when the smartphone was possible, and everybody started getting smartphones and so forth. And then I just talked about 5G. Well, 5G also uses OFDM. So OFDM, excuse me, OFDM is very good, has settled in as a very powerful wireless air interface. But the orthogonality of it causes some issues in terms of utilization of spectrum. And so one of the ways of getting greater capacity is to allow spectrum sharing in some way. And CDMA back in the 3G was an idea like that, but it wasn't quite the same as what's being proposed for 6G, which is non-orthogonal multiple access, which is a new paradigm for allowing multiple users to share the same radio resources at the same time. NOMA is part of 5G standard for certain applications, but we expect that we'll see more NOMA in 6G because there's so many applications where we just need much greater use of the spectrum. Another one is spectrum sharing. So, of course, NOMA is a way of allowing users to share spectrum in an organized way. Spectrum sharing is another way where multiple users not using NOMA, but using their own network share spectrum that's idle, that's been idled by other users. So we've already been talking many years about cognitive radio, which is a way of allowing secondary users to use idle spectrum of incumbents in given band, primary users, But now we're talking about dynamic spectrum sharing among users who are peers, okay? And this we could think about doing in the unlicensed band, okay? And rather than just sharing spectrum, you could also share some of the networking equipment. So this is called symbiotic radio. And there's been a lot of work on this in recent times as a way of supporting massive access. So here, again, AI becomes very important because when you start having these very complicated radio environments with, having to do sharing, and the decision-making processes are quite complicated. So in order to support dynamic spectrum management, we need to go beyond model-based spectrum management techniques. So AI here enters in another place here. Some other issues that we might think about is the use of blockchain to help manage wireless access and networking. And I think blockchain, it's a technology that allows zero trust transactions. So it could be used for IoT, for sharing spectrum. It could be used to run smart contracts among different IoT devices that don't necessarily trust one another. And for things like authentication and control in a trust-free environment. So the idea behind blockchain, it allows us to, as I said, produce trusted physical links in a sort of a zero trust environment using the blockchain. And it can support various services, and particularly it might support something like federated learning, which is the type of edge learning where multiple learners, edge devices, work together to learn a common AI model. Some of the big challenges with blockchain are latency, because I think you may know that blockchain is very slow, and scalability. And we've been reading a lot in the news about the energy usage of blockchain. So there are a lot of issues. Blockchain is a big research area, and some of these issues are being addressed. Another area of potential advancement is cell-free Mimo. So I mentioned Mimo at the beginning, and at 5G, we have massive Mimo. Today, Mimo is implemented on a single transmitter, but one way to enhance the number of antennas and enhance the performance is to combine different base stations or access points for one downlink session to take advantage of the distributed nature of the antennas that would be distributed over multiple access points. This is a way of, goes also under the name of cloud radio, and it allows you to control tightly intercell interference and other impairments that give you it might be a way of providing these terabit per second download speeds that we're talking about earlier. Some of the challenges of cell-free Mimo, very high implementation complexity, has to be done in the cloud. That means there's big front haul and back haul requirements, getting data up to the cloud and back down. There's a lot of problems with figuring out how to synchronize channel state information and provide channel state information, which is needed to take advantage of the computations, and also latency, backhauling data into the cloud for the computations needed to take advantage of this architecture. So there's a lot of research going on. A lot needs to be done here before this can be practical. There are a lot of other technologies in the physical layer, which I won't necessarily talk about today, but autonomous unmanned aerial vehicles, drones. That's a new way of providing coverage in areas where we don't necessarily have other coverage. So it's quickly adaptive, it's mobile, you can send in UAVs to an area, create a hotspot, and so forth. Reconfigurable intelligent surfaces. These are meta surfaces that allow you, for the first time really in the history of radio communications, allow you to tune the radio channel, the radio environment. So in the past, we basically, when you're given, you've got a transmitter and receiver, between them, there's some radio channel and there's not much you can do about it. You've got multipath and so forth, creates fading and what have you. But with a reconfigurable surface intervening, you can actually tune the radio environment. So this is a promising technology as well. It's like, in a way, it's like a relay system on steroids. That is, you can really do relaying, but in a way that also controls the radio environment. Integrated sensing and communication. I alluded to this just a bit before, but here using the same spectrum and even the same, maybe the same waveforms for both sensing and communication. So you can think about radars on your car, also you communicating with base stations along the highway, all in the same spectrum using the same waveforms and so forth. So there's a lot of moving parts here, a lot of things going on, a lot of research in these areas right now. We'll see which ones of them pan out for 6G. Now at the networking level, we're also going to need a lot more flexibility than we have today, both sort of in real time, but also as networks evolve. So one of the ways of thinking about that is through software-defined networking. That is, implementing all the networking functions on general purpose hardware. Okay, so that allows you to have greater flexibility. You can program the architecture, make it much more, the network architecture, make it much more agile. It's also more cost effective because if you want to upgrade the network, you don't have to pull out old gear and put in new gear. You just have to download new network software. So this is a real game changer in terms of how networking can be operated in the future. One of the key enablers is network function virtualization, where all the functions of the network are transformed into software. Again, as I said, they can be run on the top of general purpose hardware. And that makes the network simple and elastic and adaptive. On the other hand, it's still a challenge. It's not quite where special purpose hardware is. And so there's a lot more research needs to be done to make this work well. Another aspect of the architecture is computing. We could think about, I mentioned virtual reality and, the high computing needs there. Now, if you want to do computing in the cloud, you're going to have all the compute power you need, but you have to worry about latency, high delay, back in the getting data back up to the cloud and then results back down to the edge. Okay. So another paradigm is to think about so-called multiple access computing or multiple access edge computing, MEC, where computing is pushed closer to the edge. So there's sort of edge computing where computing is done in standalone mode all the way at the edge of the network. And then there's fog computing where you have multiple layers in the network where computing is distributed throughout multiple layers of the network. So there's sort of two extremes, which is edge and cloud. And then there's fog, which takes advantage of things in between the two, or maybe some of each. So, if you have all these computing resources available to you, then depending on the application, you can dynamically allocate computing tasks. So if you need something that has low latency, you do that at the edge. If you have something that needs to have a lot of computing power where you don't care much about latency, you can do that in the cloud. and so forth. So this could be done on the fly, for example. That is adaptation to the computing resources. So those are some of the enabling technologies. Let me talk now about the few paradigm shifts. So 4 of them that I want to talk about, I already mentioned the first one, which is space, air, ground, sea integrated networks, where we look at the different networks we have, satellite networks, drone networks, traditional terrestrial cellular networks, maritime networks, and integrate them together. I'm going to say more about each one of these in a minute. And then another type of integration is across spectra. So, right now, most networks are microwave networks, that is below 6 gigahertz of bands. But we moved into the millimeter wave. This gives us better, higher capacity and greater density. And that's happened already in 5G, that's rolling out. So the next step is to go to terahertz, which is the band above millimeter wave. And that gives us even greater capacity and so forth. And this is where technology is being developed today that might enable some 6G capacity. And then optical networks. So for example, and I mean free space optical networks. So optical wireless. So things like Li-Fi, where you have, for example, LEDs being modulated in your lighting system to communicate with your laptop, for example. I'm going to take more about that in a minute. Intelligence endogenous networks, that is putting AI throughout the network. And then another issue is network security, okay, security and privacy. Whereas in the previous networks, security has been mostly an add-on to existing networks, not a fundamental in design criterion. Security by design, privacy by design, these are things that we should expect to see in 6G. So let me just talk briefly about each one of these. So the objective of integrating space, air, terrestrial networks, and so forth is to provide truly ubiquitous coverage, okay? So, different kinds of networks have different advantages. So satellite communications can give you seamless worldwide coverage, but there's greater latencies and so forth. Drone communications can give you great flexibility, as I mentioned before, mobility, adaptive altitude. You can deploy drones very quickly in areas that need extra capacity, like disaster zones. In maritime communications, well, it covers, the oceans cover 70% of our surface. So, this is a big area to be covered. So some issues that come up though, so all these are different networks today. So some of the issues that come up are, how do you make them work together? How do you make them interoperative? How do you do that efficiently? Different networks have different properties, as I said. The amount of energy consumed, the latencies, the data rates, they're all different for all these networks. They all have their own routing systems and so forth. So we need networking. We need networking protocols. We have to think about energy efficiency. What's the most energy efficient way of using these networks and so forth. So it's a very, very complicated networking problem when you have all these different parameters, all these different networks with many different capabilities. So here's one of the places where software-defined networking could play a big role, because then you have very quick adaptivity of networking structure. And so if you have dedicated hardware, it's going to be very, very difficult to combine all these networks into one and make them work seamlessly. So similarly, we can integrate across spectra in addition to integrating across types of networks. And of course, the objective here is just to meet the 6G service requirements. That is the data rate, the latency, and the density of coverage and so forth. So each of the bands I mentioned has its own advantages. So microwaves, they get wide coverage. We already have cellular systems covering a lot of the Earth, certainly a lot of the land mass of the Earth. And one microwave base station can cover kilometers of space. Millimeter wave, you get much higher bandwidth up in the millimeter waves and higher capacity than microwaves, but they have shorter range, which can actually be an advantage because then you can pack in base stations more closely. And the next step up in frequency is terahertz, okay, hundreds of gigahertz. And you get even larger bandwidth. There's better security performance because you get very tight beams. You can form very tight beams with multiple antennas and so forth. And then in the optical bands, and again, here I mean free space optical, easy containment. You don't have a lot of leakage from, say, a Li-Fi device, easy to control the radiated signals and so forth. Plus, you already have infrastructure installed. That is, you already have LED lights, and all you have to do is to figure out how you want to connect them to the network to modulate them. Some issues that come up, one is modeling all these channels. Traditionally, we've designed coding schemes and receivers and transmitters and all those things based on channel models. So we need to know how the channel behaves. We know pretty well how microwave channels behave. We're learning how millimeter wave channels behave. Preliminary measurements are telling us that terahertz channels are very similar to millimeter wave channels. Of course, optical, we also have some models, but we still need to know more. And we also need to create metrics for spectrum usage. If we're going to integrate the spectra, we need to know, that means we're going to optimize which piece of the spectrum we're going to use for a given communication session. So we need to have some metrics so that we can optimize that, okay? And that would support spectrum resource management in an efficient way. So here is an area where machine learning can play a big role. First of all, machine learning for doing channel modeling, and also for managing the spectral resources. Okay, so here's another place where machine learning can play a big role. And speaking of machine learning, intelligence endogenous networks. So here, the objective is just to incorporate intelligence and adaptivity throughout the 6G network, okay? And so, a lot of things can be done with AI. One is to analyze the user population, optimize services, trying to figure out the environment, so channel modeling and so forth. And it also can be used for very complicated visual and image processing, which has been a very big success story of AI already. Decision making, dynamic control, these are all things that machine learning is good at. So putting more of this in the network can be a way of making it more effective. There's a lot of complications. A lot of machine learning algorithms are for very specific, well-defined tasks. Some image recognition, recognizing something in an image, or something like that, making a very specific decision. But if you think about how complicated a network is with all the different layers and so forth, just putting that together in a knowledge graph is quite daunting. And then the corresponding mechanism design to evolve the network becomes much more complex as well. So this is taking machine learning to a new level, basically, where you have a very, very complicated machine learning problem, goes well beyond the kind of machine learning problems that many people have studied so far. And then finally, I'll just mention security and privacy. So one issue with using more AI is that it itself brings up security and privacy problems. AI software is vulnerable. It's well known that you can, there are poisoning attacks and so forth on AI systems. Even if you think you have privacy if you don't share your data, if you share a machine learning model, you're basically sharing something derived from your data. So privacy can leak through AI training. And again, AI software can be vulnerable. It's software, it has bugs and so forth. So, there's a lot of issues brought out by using more AI. That is, you get the flexibility, say, in software-defined networking, but the counterpart to that is you're more vulnerable as well. And then IoT, where we have massive numbers of devices, and these devices are not going to be, smartphones. They're going to be sensors or actuators or very low cost devices. They're not hundreds of dollars like a cell phone. They're $10, that kind of thing. They don't have the computing capability, the energy, the storage, or anything to support complex cryptographic primitives. So that means that these devices are going to be very hard to authenticate, very hard to secure. And so that means some fraction of them are going to be malicious. And that means IoT systems are going to be vulnerable to malicious actors. I'll say a little bit more about that briefly in a second. Some solutions are lightweight crypto. There's a lot of that being developed. Physical layer methods, I'm going to say a bit more about that before I wrap up. Quantum in the same decade that we're talking about here for 6G development, quantum computing is going to come into its own. So there's going to be a whole rash of new security issues because of classical crypto algorithms are going to start being broken by quantum machines. And then I mentioned blockchain already as a possible solution for zero trust environments. So I want to just say a little bit about physical layer security. What is that? And then I'll wrap up. I'm about out of time. I have about a little more than 5 minutes. I'll take about 3 of them for this. So first of all, what do we have today? How are wireless networks secured today? Well, typically they're secured at the higher layers of the network. So if you're not familiar with this, engineers like to think about networks as being organized in layers where each layer has its own function. So the physical layer is the actual physical medium. So in the case of a wireless network, it's the ether. And then there are layers above that. The network layer, for example, does routing. The application layer is where we interface with the network, so web browsing, talking on the phone, what have you. And today, security is mainly provided at those higher layers, typically at application layer or the transport layer, so-called transport layer. And why do we need to worry about this? Because this works well. Today, we're not afraid to do banking on the internet. We're not afraid to be talking like this over the internet. So it works well. We use our cell phones with confidence. We use our laptops with confidence. And why does it work well? Well, it's widely deployed. It's been tested. It's very trustworthy. As far as we know, there are no feasible attacks. If you have a long enough key, it confounds any computational attacks. But there are some disadvantages of standard cryptography. One is it's built on unproven assumptions that certain mathematical problems are too hard computationally. Those could fall by the wayside if quantum computing comes into the forefront. It's computationally intensive, so it's, as I mentioned, for IoT devices, it may not be possible to run typical public key type systems. And it requires infrastructure. You need key distribution and other things, trusted parties and what have you, that what may not be possible when you have very light infrastructure like you might in some IoT system. So physical layer security provides security based on the physical properties of the communication network. So in this case, the physical properties of the radio channel, the radio environment. And it's based on information theoretic proofs of security. So it's quantum secure in the sense that it doesn't rely on any difficulty, any computational problems. You can generate secret key from the radio environment by distilling key from the radio environment. And it's fast and lightweight. That is, it has the same complexity of error control coding, which is basically on every communication device. But there are some disadvantages. First of all, it relies on some assumptions about channels. It doesn't rely on assumptions about computation, but it relies on assumptions about channels. It's an asymptotic, based on an asymptotic theory largely, although that's being challenged now. And it's not really proven. It's not like the kind of crypto we're used to after 30 years and so forth of cellular networks. It's really still in its infancy, even though there are some prototype systems out there. So why do we care though? Well, I already mentioned Internet of Things. IoT devices can't really necessarily support standard cryptographic and other related security primitives that we use today with our smartphones or our laptops, okay? And the number of those devices is greatly outstripping the number of cell phones. There's only 7.5 billion people in the world, so the number of smartphones is upper bounded by that, but there's gonna be many, 10 times more, maybe 100 times more IoT devices. So that's where the security frontier is gonna be. Just an example, this comes from a paper we did USNICS a few years ago. We looked at what could happen if you could compromise IoT devices in the home. So things like what we call like Nest devices that control your water heater, your refrigerator, and so forth in order to optimize the energy usage in your home. So that's an example of IoT. And those are not very well secured, and they rely on the consumer to actually change the password and so forth. So we did a study showing that a botnet that could control 600,000 IoT devices, which by the way is practical. There is an example. The Mirai botnet was a 600,000 bot attack on European internet, successful attack. If you have a botnet of that size attacking IoT devices on water heaters, you can change the demand on the grid by 3 gigawatts instantly. That is, turn them all off or turn them all on instantaneously together, 3 gigawatts, which is like turning the largest currently deployed nuclear plant on or off instantly. And of course, if you know how the grid operates, it's balanced, load and generation is balanced at all times. That would cause the tripping of generators. It would cause cascading failures. It would be a disaster for the electricity grid. So, here's an example that it's not going to happen tomorrow, but there could be a time when there's 600,000 homes with water heaters controlled by IoT devices, and then a botnet could get out there and make this thing. So we need to worry about this, I think, is the bottom line of this example. So physical layer security is a way of doing lighter weight security. It's not necessarily as bulletproof as crypto, but it's in a way a kind of a best effort type of security, but it allows us to think about quality of security as a parameter in the design of networks, just like quality of service came into the design of networks 20 years ago. Now, quality of security needs to come into networks as another parameter. And, if you want ironclad bulletproof security for banking, you better use crypto. But if you have an IoT network, you can't use crypto. You better do the best you can and look at what quality of security you can provide by using the physical layer. So that's basically the idea here behind physical layer security. This is an area that I'm interested in personally, and so I think there's a lot of future for this. And there's a lot of work in industry and in academia in trying to realize these ideas. So let me out of time now, so let me wrap up. So first of all, what have I talked about today? Well, talked a little bit about why we need to think about 6G. Then I talked about some of the performance metrics we need. I talked about some of the enabling technologies in the air interface and in the network. And then I talked about some of these paradigm shifts. And then I did a little bit of a deeper dive into the idea of designing in security and using in particular the idea of physical layer security. And with that, I'm done, and I'll thank you, and I'll be happy to take questions if there are any. I see there's some things in the chat. Let me stop sharing. I can go and look at the chat here. So
thank you.
I don't
Thank
know,
you very
Manoj,
much.
do you want to handle the questions, or would you like for me to go through?
Whichever one, 3 or 4 questions you feel like answering, that would be great.
Okay,
yeah.
Let's see what we got here. Okay, there's a question here. It's Nitin Sali. Whether 6G or higher is affordable to the common man in the world. So I think the question is about affordability. And, you know, one of the big movements in networking today is inclusiveness. And you may know that, for example, our president, Joe Biden, has talked a lot about expanding, you know, internet coverage into rural areas. So, you know, I think, you know, some of the services may not be affordable. I mean, I think, you know, I have an iPhone, you know, I think that's pretty people in some parts of the world. But lower cost type of networking devices, I think are, you know, people have thought about them. And I believe that, you know, inclusiveness is something that is in the minds of network designers and deployers and governments. So I think this is an issue. I mean, I think there are many people who aren't served well by networks. And I think that's one of the things we have to think about. You know, this is in many ways is a political issue, but it's also a technical issue, developing lower cost technologies. And, you know, I think a few years ago, there was a big push to create really low cost laptops that could be, you know, more easily purchased by people from poorer regions. So yeah, I think, you know, this is something that people are thinking about, but we still need to work more about this. There's a question here about visible light. So would visible light communications play any role in 6G? And I think, you know, this is still, of course, we're just speculating, but I think, yes, I think, you know, certainly I mentioned it just briefly, you know, so-called Li-Fi systems are visible light systems where you modulate LED devices with communication signals. So the human eye, you know, its modulation rates are, you know, gigabit per second. The human eye doesn't even detect that, right? It's like on your television is really flickeringness, but you don't detect it at all. And so it wouldn't affect the lighting quality, but you could use that modulation to, with a receiver on your laptop. For example, I'm sitting under a light now. I could have a receiver on my laptop. The LED bulb up there could be modulated and I could be communicating over visible light. So I think, yes, there are some challenges and that isn't necessarily the way the community has been going for 5G, but certainly it's a resource that shouldn't be overlooked. And there's a big research area there. Let's see. So in my opinion, what challenges and development can we expect in data storage and security while transforming from 5G to 6G and beyond? Okay, well, I think this is something I might have addressed after you wrote the question, but you know, I think the key thing here is to think about security as being, you know, a first principle of design rather than an add-on. You know, it's an applique now. You design the network for high-speed transmission, and then you add something to it, like crypto or something like that. And I think we need to get away from that thinking and start thinking about, as I mentioned at the very end of my talk, quality of security. So we have quality of service, which talks about data rate, latency, and so forth. And we need quality of security. What level of security do you want? Do you want zero trust security, where you don't trust the network at all, or do you want to allow some potential leakage? You might think about, for example, a content distribution system, where if you're distributing content, which people have to pay for, if some of that leaks to somebody, it's really not a disaster. And in fact, if you can just disrupt leakage, for example, if you have a movie that people are streaming and somebody's you have a subscription service and somebody's who doesn't have a subscription can intercept part of that movie, it's not that useful to them, but unless they can see the whole movie. So as long as you can disrupt that, 50% of the time, you've done your job. Whereas with banking, you want to disrupt 100% of the time any kind of intrusions into the network. So, I think this quality of service, quality of security is something that's important. And I think we need to design it into the network rather than adding it to the network after it's been designed. So I think going from 5G to 6G, that's an opportunity that we have. Yeah, so the next question has to do with a technical issue about the adaptive equalization and classical channel estimation, based on sample covariances and so forth, and how the shorter coherence, some of the new parameters of the channel of 6G channel and the shorter packets you need for low latency might affect that. And I think this is a very important issue. I mean, at the fundamental level, there's a lot of work on non-asymptotic information theory today, trying to understand what are the fundamental limits at very short packet lengths, which is what you have in IoT type applications. And together, what goes with that is, of course, channel knowledge. So the more you know about the channel, the better you can do. But it's very hard to understand the channel if you have short coherence time, for example, with high-speed vehicles and so forth, like for autonomy, autonomous driving. And so there's a lot of work to be done. I don't think we can just apply necessarily what we've done in the past to these new systems. Hope that answers the question. Yeah, so let's see, I think I've answered that one in my talk. So let's go. Yeah, here's another one. So this is a good one. I didn't mention this much. What will be the possible environmental effects of 6G communication? That's a good one. Telecommunications uses a lot of carbon, but there are movements, and there's certainly a lot of research on energy harvesting, meaning using the energy that's around us in the environment to run our communication networks to a certain extent. So solar, wind, radio, for sensors, you can, absorb energy from the radio environment. There's a lot of radio energy around us that's enough to power sensors and so forth. So that's important, and I think that's a big issue. Now the next question right after that one is related, which is how can global warming concerns be addressed using deep learning on massive data sets? So that's another side to this, aside from the amount of energy that the network does not consume on its own. These massive connectivity gives us unprecedented sensing capability, you know, we can look at what's happening all over the place in terms of heat maps and other kinds of environmental factors that will affect, you know, CO2 concentrations, things that will affect warming. So the network, and aside from its own energy consumption, which is an issue that needs to be worked on and is being worked on, there's also the idea that using the network in the application of environmental sensing, which is certainly, you know, a great application, and I think you know, it's something that people are going to be taking advantage of going forward. It's a good question. Yeah. Oh, so yeah. All right. Let me just go ahead. Let's see. Yeah. So here, I'm going to just take one more question. I think the others I may have addressed in my talk after they came in. So this has let's see. I think the issue of having limited data. Okay, I'll just comment briefly on this. So, you know, if we're going to put AI out at the edge, say if you're going to do AI on your smartphone, you know, you're only going to have limited. It's not a big data problem; it's a small data problem, right? So, one of the issues that I'm interested in here, we're doing some work here at Princeton in this area, is you know, model-based machine learning. So instead of just having a black box where you take data and you learn from the data, so completely data-driven, you have a model, but the model isn't accurate in certain ways. And so you take advantage of the model in the machine learning algorithm, either through its structure or something else. So an example is deep unfolding, which is a way of putting each, like having an adaptive algorithm and letting each layer be part of the adaptive algorithm. So, you know, you know something about the structure, but you either for complexity reasons or because there's some uncertainty in parameters, you still want to use machine learning. So that, I think that's a way of getting around the data sparsity issue at the edge. So I think Manoj, if that's okay, I think that's
Sure.
there's a few other good questions, but I think maybe the audience is
No.
it's late over there. So maybe it's time
Yeah, it's about dinner time. Yeah, thank you very much, Professor Vincent, for sparing your valuable time and taking up nearly all possible questions and enlightening us about the various aspects and applications of machine learning in a different branch of electronics engineering. So, on behalf of the National Academy of Sciences India Delhi chapter and the host institution, I would like to thank you once again, and also to all the attendees who have been there with us. It's late evening, it's just dinner time in India, and their presence for this particular talk at least shows the passion and the zeal for learning these new dimensions and new emerging areas in science and engineering. Thank you very much, and hope to see you maybe next year in India.
Delhi.
Yes.
Yeah.
Thank you. Thank you very much.
Thank you very much. Thank you all for attending. Thank you so much for your questions. I think there's some very insightful questions, and it was quite a pleasure and an honor to be speaking to you. And I hope you all enjoy your dinner. I'm going to have another coffee.
Sure. Okay. Bye-bye.
Bye-bye.
Bye.
Bye.